Hello everyone. I hope you're okay, and I hope that guys the videos will keep uploading and helping you out. This is the fourth video, guys, which simply means I'm doing question number 4, and these questions are all extracted from past exam question papers, né, guys? So it's very important for you to watch this video and all the other videos where I'm checking past past exam question papers with regards to Doppler effects, né? Knowing how to tackle exam-like questions will give you an edge whenever you are writing an exam. So please, guys, please do share this video to your peers. I believe that it will help them a lot. Okay, we are told that a sound source is moving at a constant velocity past a stationary observer, and then the frequency detected as the frequency detected as the source approaches an observer is 260 hertz. The frequency detected as the source moves away, from the observer is 1750 hertz. Take the speed of sound in air as 340 meters per second. Okay. Firstly, we are being asked to name the phenomenon that describes the apparent change in frequency detected by the observer. That phenomenon is simply Doppler effect, né? Doppler effect. Okay, state one practical application of the phenomenon in question 6.1.1 in the field of medicine. They use it for a sonogram, né? They use it for a sonogram. And then 6.1.3, they want us to calculate the speed of the moving source. Okay, there are two things that we know over here, guys. Né? Firstly, we have our source. This is our source, and this is our observer. Our observer, né? So what basically happens here is that the source will move towards the observer, and then the source will move away from the observer. Are you together? So the observer will detect two different frequencies. As the source is moving towards the observer will detect a higher frequency, and when the source moves away from the observer, the observer will detect a lower frequency. Are you together? So there are two things that we don't know here, guys, né? Because we do know the frequency detected, whether the source is moving away or towards the source, the observer rather. Are you together? But we do not know the actual frequency emitted by the source, as well as the speed of the source. Are you together? So this question, guys, will require us to use a simultaneous equation. Are you together? You must have information for towards and also information for away. They shouldn't be this close. For away. Are you together? Please note that, guys, the formula for towards, before I even write down the data, yes, the formula says FL is equals to V plus or minus VL over V plus or minus VS, times the frequency of the source. But since we know that our listener or the observer is stationary, it simply means the velocity of our listener is equal to 0. So it simply means that our numerator will simply have the speed of sound in a medium only. And then for the denominator, since the source is moving towards the listener, I will simply have V and the velocity of the source. But since the source is moving towards the listener, I will have a minus there at the bottom. Are you together? And then obviously multiply by the frequency of the source. Are you together? For the away movement, frequency of the source, the listener is stationary, so the velocity of the listener will be 0. My numerator will be V as well. I'll simply have V and also Vs multiplied by the frequency of the source. But now, whenever the source is moving away from the listener, our denominator will have a plus over there. Are you together? It's minus whenever it's moving towards and plus whenever it's moving away. Are you together? Okay, now let's calculate. We are given data, né, guys? For our data, we are told that frequency of the listener, the frequency detected is 2600 hertz. We don't know the frequency of the source. The velocity of the listener, the guy is stationary, or the listener rather is stationary, so it's 0 meters per second. We do not know the velocity of the moving source as well, but the speed of sound in air we're given to be equals to 340 meters per second. That's 340 meters per second. Are we together? Okay. From this information, we can have an equation. I know that FL is equals to V all over V minus VL, all multiplied by frequency of the source. That's 2600 is equals to 340 all over 340 multiplied minus the velocity of the source. Are you together? And then I have frequency of the source over there. I can just cross multiply. I'll simply have 2600 multiplied by 340 minus Vs. This is equal to 340 multiplied by the frequency of the source. And this will be my first equation. Are you together? And then now let's focus on the away information. The frequency of the listener is 1750 hertz. It was given to us. We don't know the actual frequency of the source. We know that the listener is stationary, so their velocity will be 0 meters per second. We don't know the velocity of the moving source, and the velocity of the speed of sound is just 340 meters per second. From this information, we can declare that we can say that FL, which is equal to V over V plus Vs times Fs, is equal to 1750 times is equal to 340 over 340 plus Vs multiplied by Fs. Obviously, whenever I cross multiply, I'll simply have 1750 times 340 plus Vs is equal to 340 times Fs. 340 times Fs. 340. And this will be my second equation, equation 2. Now I have equation 1 and equation 2, and both of them are equal to 340 Fs and 340 Fs. So it simply means that equation 1 is equals to equation 2. Are you together? So I can just simply equate the two. I'll have 2600 340 minus Vs is equals to 175. What do I have there? 340 plus Vs. All I need to do now is to just remove my brackets first. Whenever I multiply there, 2600 multiplied by 340, this will give me 884,000 minus 2600 Vs. Are you together? And then 1750 times 340, this will give me 595,000 plus 1750 Vs. Are you together? Now all I have to do is to group the like terms. On the left hand side, I'll have 884,000 minus 595,000 is equals to 1750 multiplied by Vs plus 2600 multiplied by Vs. On the left hand side, I'll simply have 884 minus 595000. This will give me 289,000 is equals to 1750 plus 2600. That's 4350 Vs. Divide both sides by 4350. Therefore, the velocity of the source, that's 289,000 divided by 4350. This will simply give me 66.45 meters per second. So that's the actual velocity of the source, ne? It's the speed of the source, of our moving source. We simply got 66.45 meters per second. Okay, will the observed frequency increase, decrease, or remain the same if the velocity of the source increased? If the velocity of the source increased, will the velocity increase, decrease, remain the same? It would increase over here when the source is moving towards the observer, and obviously decrease when the source is moving away from the observer. Okay, and then now we are told that spectral lines of star X at an observatory are observed to be redshifted. Explain the term redshifted in terms of wavelength. When the star, guys, is being redshifted, it simply means that it is moving away from the Earth, and hence the universe is expanding. So the distant star will have a greater wavelength. Why? Because anything that is redshifted, red has a lower frequency, guys. Ne? So anything that is redshifted has it simply means that it has a lower frequency and a greater wavelength. Are you together? So the star will simply have a greater wave length. Are you together? And then now, will the frequency of the light observed from the star increase, decrease, remain the same? It will decrease, guys. Are you together? Why? Because our star is redshifted, so the frequency has to be lower. That's how, guys, you're supposed to tackle this question. Just stay tuned and wait for more videos. Thank you.